Watch what happens when this bowl of bright blue liquid is slammed with a high-speed punch. Instead of splashing everywhere, the surface instantly turns rock hard, and the fist bounces right off. But if you take that same hand and press it down slowly, it sinks into the bowl effortlessly, just like dipping your fingers into a pool of water. This mixture is entirely made from two everyday ingredients, plain water and ordinary cornstarch. It forces us to ask a pretty basic question: are we looking at a solid or a liquid? We are taught early on that materials have specific rules. Water splashes, rocks don't. A material that can do both based on how you touch it challenges our standard definitions of how the physical world operates. This diagram shows the classic rules for states of matter. In a solid, like ice, particles are locked into a tight grid. In a liquid, like water, particles are packed loosely, leaving empty space for them to slide past one another and flow. To understand our cornstarch mixture, often called Oobleck, we have to look at the massive size difference between its ingredients. Under a microscope, cornstarch granules are massive, jagged boulders compared to the tiny water molecules around them. Because there is so much cornstarch packed into the bowl, those giant particles crowd almost all the available space. Because it is so tightly crowded, Oobleck spends its entire existence teetering on the absolute edge. It is one tiny push away from acting like a flowing liquid or a rigid solid. The deciding factor that tips Oobleck over that edge is physical force. When you apply a very low amount of force, like slowly dipping your finger into the bowl, you are giving the mixture plenty of time to react. Moving slowly gives the tiny water molecules time to act as a perfect lubricant. They coat the massive cornstarch boulders, acting like microscopic ball bearings that let the jagged edges glide smoothly past one another. As long as the force you apply remains low, those giant particles never crash, ensuring the mixture flows like a true liquid. But what happens when the mixture takes a sudden, massive impact, like a heavy steel ball dropped from above? For years, scientists debated exactly why the fluid hardens. Recently, researchers at the National Institute of Standards and Technology measured how force is actually pushed through the mixture at a microscopic level. They found it all comes down to a shift from smooth lubrication to harsh, grinding friction. A sudden impact squeezes water molecules away. Without this buffer, jagged cornstarch particles crash together, interlocking into a rigid grid that instantly becomes solid. Once pressure is removed, friction vanishes, water seeps back, and the solid melts into a puddle. Centuries ago, Sir Isaac Newton observed that fluids follow a strict set of rules. He believed that the thickness of a liquid, how much it resists flowing or being moved, should only change if you heat it up or cool it down. This split-screen chart illustrates exactly how Oobleck breaks that rule. If you hit water with a hammer, its resistance stays perfectly flat on the graph. It just splashes. But when you strike Oobleck, the chart shows its resistance shoots straight up purely because of the physical force. Because the thickness of this fluid depends entirely on the force you apply to it, rather than the temperature, scientists classify Oobleck as a non-Newtonian fluid. Engineers are now taking that exact mechanism of friction locking under stress and moving it out of the classroom and into the world of high-tech design. Material scientists are currently designing lightweight, highly flexible protective gear filled with fluids that respond specifically to sudden, high-speed impact. When the person moves normally, the armor flows like a liquid. But if it is struck by a fast-moving projectile, the sudden force makes the internal particles lock together, hardening the armor instantly to absorb the blow. Cities are even testing smart speed breakers. These are flexible tubes filled with this force-sensitive liquid. A car slowly rolling over the bump pushes the liquid aside gently, keeping a smooth ride. But a speeding car hits it with much higher force, causing the bump to turn rigid and jolt the driver. A simple mixture of water and cornstarch shows us that when we look closely at the microscopic space between particles and understand how they react to force, we can engineer materials that adapt perfectly to the world around them.